Welcome to the DSA series. In case you're wondering what you're doing here, I'm sure you're interested in DSA, data structure and algorithms, which is why I've stumbled upon this video. In case you're wondering who I am, my name is Kallol Bhattacharya, and I have been in the IT industry for the past 24 years, recently retired. And I thought that my knowledge in the IT industry is best put to use if I am with you and I'm trying to impart whatever I have learned in terms of these lecture series. DSA, Data Structure and Algorithm, is going to be an exciting series, and we will cover everything from the basics of DSA to the advanced concepts of DSA. We will cover a plethora of questions that are typically asked in the university curriculum. So anybody who is interested in DSA as a topic, as a subject, anybody who has DSA in their university curriculums, they can definitely benefit out of this. Be with me. I'm sure this is going to be an exciting journey in order to prove how and what modern algorithms can do. Thank you so much. Hello, welcome back. This is the third lecture in the series of DSA. We cover time and space complexity today, and we have been touching upon the module 1, which is similar to any university curriculum that you might be having in the DSA series. The yellow font items we have already covered. In case you're wondering where those videos are, please have a look in the playlist. You should be able to see those lecture videos on the yellow fonted items. We are today discussing time and space trade-off, and that would typically complete around 90% of what we wanted to cover in unit or module 1. After this, we will be covering asymptotic notations and the linear search and binary search, explaining the asymptotic notations in line with the applications. That's going to be the next video in the series, which would complete module 1. On this particular lecture, we are starting off with the time and space complexities, and we would discuss mostly around time complexity. We will touch upon space complexities in the first part of the video, and then we'll proceed on with deep diving into multiple items and multiple function classes of time complexity as we go forward. That being said, this is what we will do. We will cover first what do we mean by an order of an algorithm. Then we will cover the various conventional orders. Conventional orders are typically around order of 1 and order of n. And then we will cover about the other orders in the function classes, which would be typically your cubic, your logarithmic, your square roots, your quadratic. Those classes of orders we will cover. We will also explain you what classes actually mean, classes to functions. And then we will also deep dive into how a typical function might look like in terms of the complexity curve. And that's where we will end the lecture for this third part of the series. Now, that being said, let us get into the model of understanding the order of an algorithm. Now, first, we will have to understand why we need to understand the order of an algorithm. Now, an algorithm written for, let's say, if I write an algorithm for swapping two numbers, that swapping two number algorithm can have various models in which it can be written. We can use a third variable, which typically is using temp. We can use an XOR model also, where we can avoid using the third variable and get into swapping of two numbers. Now, if we have to judge, the keyword is judge. If we have to judge which of this is better, right, we need various mechanisms in which these two algorithms should be benchmarked against. One of those mechanisms is time complexity. One of those mechanisms is space complexity. And in the previous video, we have understood all the mechanisms in which we can judge an algorithm. So if you want, please watch out the previous video as to what are the factors in which, or what are the factors that define the performance benchmarks of an algorithm. It's a very common question that keeps on getting asked. So it's important for you to understand that in case you have skipped it. We are discussing two of those features in this video, which is time and space. With understanding the time taken by these two algorithms of swapping two numbers, we can make out which algorithm is better compared in terms of the execution time, or which algorithm is better in terms of taking less amount of space as far as memory is concerned, right? So both of these are important from judging an algorithm, and both of these is what we will see, and which is why we are trying to understand how do we judge an algorithm on the basis of time and space. So this particular next 5-10 minutes that we will cover will be mostly around understanding that, okay, we want to understand time and space, but how do we measure that time and space? How do we interpret the time and space so that we can say that my algorithm is taking this much amount of time, or my algorithm is taking this much amount of space? Now for that to be done, let us go back to our class 10 days, our standard 10, when we learned about linear equations, and let us take one linear curve which is represented by y equal to mx plus c, which I'm sure all of you are aware of. And let me take a curve which represents a linear line. So let us say that if we have a line like this, then I'm sure you would understand that we can call this as y1 equal to m1x plus c1. Can we call this like this? We can say y1 equal to m1x plus c1. And what is in this axis? This axis represents a function of x which is equal to y, and this axis represents x, right? I'm sure you are aware of it. This part of the curve is the intercept, which is your c1, right? And this part of the curve represents your slope, which is your m1. So m1 is your delta y by delta x. All this you would have learned during your class 10 days, and I hope you remember it. I'm just trying to jog your memories. If we have another curve which is y equal to m2x plus c2, then that curve, provided m2 is more than m1, will look like this, right? So, and this will be actually, let's say, c2 for that particular curve. If we have one more curve, which looks like this, y3 is equal to m3x, and there is no intercept component to that curve, then I'm sure you can understand it may look like this, which is equal to your y3 equal to m3x. Now what is changing in these graphs? These three graphs have a changing amount of slope. They have a changing amount of intercepts. Now what we need to understand is, when we talk about time complexity, we do not talk about the amount of time taken to execute a program or an algorithm. We talk about the order of time taken to execute the program. We cannot say, I'm sorry for that. We cannot say that time taken by my algorithm, which is, let's say, tx, is equal to 200 milliseconds. Yes, we can say that, but that will be applicable for a particular machine. If I give you a better machine, then don't you think you can execute this algorithm in 2 milliseconds? The same algorithm can be executed in two different machines in two different amounts of time. So how can you tell that my algorithm takes 200 milliseconds and hence it is good? You cannot say that, right? So it can be good in an excellent machine. It can be far worse when given a poor machine. So if you give me an excellent machine, I can also produce a 2 milliseconds time. But as of now, it takes 200 milliseconds in my machine. So which is where I'm trying to get at. What I'm trying to get at is that time taken by an algorithm cannot be quantified, cannot be told as this is the time taken by an algorithm, and hence you should call my algorithm as good, bad, or worse. Good, bad, and worse doesn't come with the time, actual time taken by an algorithm. Because actual time is always a function of several ecosystem of factors, several factors relevant to the hardware. So I cannot say that my algorithm is good just because it takes X seconds. So I have to tell with respect to time that my algorithm is good, but not taking the absolute magnitude of time taken. And hence I will use the asymptotic notations, which is basically saying that it takes an order of such and such value rather than saying the exact value. So we will say it takes an order of that particular value. So we will come to that as we go forward. So for now, what I am trying to hint at is that the time taken by this algorithm is typically going to be expressed as an order of the of several factors, right? What are those factors is what we are trying to see now. Now, before we go into seeing those factors, can we appreciate the fact that fx equal to y is actually nothing but what it is trying to say is that fx is actually dependent on x. The more you increase x, the more will fx also increase, right? So I hope you can understand that part of the component. The more I am increasing x, the more these lines are increasing from a y standpoint, right? So that is what is very key for you to understand, that the component of y-axis is completely dependent on the component of the x-axis. The more x-axis increases, the more y-axis will also increase. So in that case, can I therefore say that if we say that these are actually the time taken for execution of your system, can I say that this is also a function of x? The time taken is basically nothing but t of x, which is dependent on x, and x here is the keyword which says x is the number of inputs. So if I say that my number of inputs provided to my algorithm is going on increasing, then can I say my tx also goes on increasing? Of course I can say that. My number of inputs, which is x, goes on increasing, then the time taken to execute the algorithm also goes on increasing. More I give x, the more the time taken to execute the algorithm will increase. So can I therefore say that if the time taken by an algorithm is today represented by this, which is y2 equal to m2 x plus c2, can I say that if I run, and what is happening here, m2, you can see that m2 is greater than m1. What does that mean? That means that a small change of x produces a large change of y for m2. That is what it means. A small change of x produces a large change of y. That means smaller you increase the number of elements, the larger the time taken by that particular algorithm. So even for a small change in the number of items, the algorithm is going to increase its time, is what M2 is trying to say, right? So can I say that M2, the time taken for the algorithm for a small change, increases because the machine is slow? The machine does not have decent amount of power. Can I say that? Of course I can say that, because for a small increase of the number of items, if the machine takes relatively larger amount of time as compared to this, right, which means that this is not running, this may not be running, I won't say not running, this may not be running on a proper machine, it takes more amount of time. So if I switch the machine here, if I switch the machine for this graph into a better machine, will this graph not become similar to this graph? Try to appreciate what I'm trying to say. I'm trying to say that if I change m and make this m equal to m1, then this particular y2 will become equal to y1, because m2 has now become equal to m1. And what is m1 and m2? M2 and m1 are the change of time when you give more and more inputs, right? Is the change of time increasing for a particular set of inputs in the same manner as the other set of inputs? So if I give delta x, will both the curves behave in the same manner? Will both the delta y's behave in the same manner? Delta y1 and delta y2, will both of them behave in the same manner? No, they will not, because delta y1 may behave in a slower manner. In the sense that delta y1 will increase faster. That means the machine is slow. Delta y1 will increase faster, and delta y2 will be slower in change, and hence it means time taken is smaller, which means that the machine is fast. Now, can I make this equal? Of course I can make it equal. I can make this y1, run on a faster machine. So if I make this run on a faster machine, what will happen? My M1, which was, the time was increasing faster, right? My time was increasing faster for M1 for a particular set of inputs. That will increase, that will take much slower time, right? So when I say slower time, the time here, the delta here was increasing much faster. So if I draw you a better representation of this diagram, I'm sure you would probably understand. So if I have a slope like this and I have a curve like this, and you compare the slope of these two curves, let me make this a bit flatter. So you compare the slope of these two curves, you will understand what I'm trying to say. So if you see this, this is basically your delta y, right? Let me bring this here so that we can align it with this. So let me bring it here and I'll show you here. And the same graph we will take here and we will see that it goes here. So you can now appreciate that my delta y2 and this delta y1 for the same amount of delta x is different, right? So what does this signify? That if I increase my input by the same amount for both the algorithms, this particular algorithm, which is represented by this graph, will take more amount of time to execute basis the change that you have supplied to it, as compared to this algorithm, which will take less amount of time. So can I say that here the time is more and hence it is slow? Can I say here that the time is less and hence the machine is fast? And therefore, can I say that if I change this machine to run into this machine, can I say my M1 will become equal to M2? That is, my delta y2 will become equal to delta y1. And therefore, this graph will coincide with this graph. And that is what I'm trying to say in this entire scenario. So I'm trying to establish the fact that all these curves, if put on different machines, right, which are faster or slower, will always converge to one single equation that we can always bring into the situation. We can say that that one single equation is going to be represented as y equal to mx plus c. All the curves that you see at the top right here will be y equal to mx plus c, because all the curves can be executed in different speed of machines to make sure that your slope coincides with y equal to mx plus c, and hence everybody will execute themselves in the nature of y equal to mx plus c. Now if everybody executes themselves in the nature of y equal to mx plus c, then can I say that all of these will take a similar amount of time? It will take a similar amount of time, and I'm not saying that it will take 200 milliseconds, 10 milliseconds, but can I say and can I write that it will take the time taken by any algorithm, for that matter Tn, which is this, right? And I'm replacing x with n now, right? So I'm replacing x with n because it is easier to comprehend that, because I'm saying that x is the number of inputs. So instead of calling it as x, I'll call it as n, and hence tx becomes tn. So can I say the time tn that is taken by an algorithm is basically a function or directly proportional to my n? And can I say that it is directly proportional to the number of inputs in a linear manner, right? And this linear word is very important here, because what you see in a linear manner is basically these lines. It is dependent on x, everybody is dependent on x, but in a linear manner. The more you increase n, the more your time will increase in a linear manner. I am not saying that it will go like this in a parabolic manner. Here also it is increasing this particular curve. Here also we are increasing n, and hence y is increasing, right? Here also we are increasing n, tn is increasing, n is increasing, tn is increasing. But is it increasing in a linear manner? No, it's a curved parabola, right? So this is a representation of probably a quadratic a polynomial, but we are talking of a linear polynomial here as far as this particular slide is concerned. Hence, we are talking about a linear manner of increase of time as and when the number of inputs increases. So all we are worried about is only two things. One, does the time increase? So let me put it in this way. So does the time increase or decrease with more inputs, more or less inputs? This is the first point we are worried about. Does the time increase or decrease with more or less inputs? So we are not saying how much the time increases while, we are saying does the time increase? And in this case, we see yes, all the time increases with the inputs. Next thing that we are worried about is by asking ourselves, is the increase or decrease, the time increase or decrease, is it in a linear fashion? Is it in a linear fashion? And that is what we want to find out. So this is important, and this is important, this is important. Right, so this is what you need to figure out when we talk about time complexity or space complexity. We'll come to space complexity, it is similar to this, but for now we are just discussing time complexity, and we are trying to tell you that y equal to mx plus c is where all the curves can converge when it comes to a linear amount of time executed by an algorithm. We can shift machines and make sure that they execute in the same amount of time as taken by any other machine, right? So we can always shift a curve whose slope is steeper or flatter to a conventional benchmark slope, which is y equal to mx plus c. And therefore, all curves can be represented from an algorithm standpoint, from an asymptotic notation standpoint, as y equal to mx plus c if they grow in a linear manner with respect to the number of inputs. That is what we have established here. Now, if you understand this, then I'm sure you can understand the fact that if we take a particular algorithm which actually executes itself, if we take a particular algorithm which executes itself in a constant amount of time, right? In this particular algorithm, we have Tn, and with Tn, we have the number of inputs here, and we are saying that this is executing in a constant amount of time. So can we say this is C1, right? And what is C1? C1 is your y1 is equal to 0x plus C1. And what have I written? I have written something like y equal to mx plus c. That's what I have written. So this curve has zero slope, and that's why your m is 0. But it still has an intercept, which is your C1. And that is what we have represented here. Now, can I say that I can have one more curve which looks like this, which is at a C2? Can I have one more curve which looks like this, which is at a C3? Then can I say we have y2 equal to 0x plus C2 and y3 is equal to 0x plus C3? We can say that, right? And if we can say that, can we say that y1, y2 and y3 are executing in a constant amount of time and they do not have any relevance to n? N is nowhere in the picture. Your Tn is not dependent on n. So Tn is always a constant k, right? Whatever that k is, it can be C1, it can be C2, it can be C3. What are these? This may be 200 milliseconds in my machine. This may be 100 milliseconds in some other machine. And this can be 10 milliseconds in some other machine. So can I say, therefore, that I will make it a constant and say that Tn has executed itself in a constant amount of time? It does not depend. It does not depend on the inputs. It does not depend on the inputs. When I say input, it is this. So Tn does not depend on n. Tn executes itself in a constant amount of time, no matter whichever machine it executes, no matter how many times it executes, no matter whatever is the change of inputs you give, it will always execute in that machine in, let's say, 200 milliseconds of time. Hence, it is a constant amount of time, right? So when I showcase my algorithm to the entire wide world, I will tell them that my algorithm executes in 200 milliseconds? No. I will tell them that my algorithm executes in a constant amount of time. No matter however you change the number of inputs, my algorithm will never change. It will always execute in a constant amount of time. So that brings me to the topic where I wanted to establish that when your algorithm is executing in this particular order, in the sense that Tn was proportional to the number of inputs in a linear manner was because it was following this graph y equal to mx plus c, then the degree of this particular polynomial is actually 1, m to mx, I'm sorry, not this one, we have the one here, the power of the independent variable, which is your x. The dependent variable is your y, the independent variable is your x. So the power of the independent variable in this case is the degree, which is 1. So can I say that my polynomial or my time will be whatever that time I'm going to take for my execution of this particular polynomial, of this particular algorithm, is going to be a function, my time will be a function of n, because it depends on n in a linear manner, right? So what is the equation coming to? Y or Tn, it is coming to like this. Tn is equal to, we will say that Tn is equal to mn plus c. This is what we will say. So can I say, therefore, Tn is a function of n? From here, I can definitely draw the conclusion that Tn is a function of n. Now, if I say Tn is a function of n, and I said n and not n square, n cube, because the degree of n here is 1, right? So, and I said that in this manner. Now, if I say this, can I rephrase this and say Tn is basically an order of n? The time taken, because it is a function of n, is an order of n. The more you give n, the more Tn will increase. So it is an order of n, right? So if I can say this, then can I say that if my algorithm is proportional, the time taken by an algorithm is proportional to n square, right? Instead of being proportional to n, then of course I can say that my algorithm has an order of n square. So I can say that depending on what the polynomial the algorithm time represents, asymptotic time represents. So if I have the time taken by the algorithm following this particular curve, right, I can say that here x, the power of x is actually 1, and hence I will represent my algorithm as an order of another order of n, right, because x is represented as n and n has the power 1 in this particular scenario. Hence we have the algorithm time complexity of this algorithm as an order of n. The more you increase n, the more the algorithm will increase in a linear manner because it is order of n. If I have y equal to if I have y in this format, let's say ax square plus bx plus c, then we have a quadratic equation. So can I say here that the highest order here is, this order is 1, here we have a 0 order of x, here we have a 2 order of x, highest order is 2. So can I say that this will execute as an order of n square, right? Where I will say that the more I give n, y will increase in a square manner as and when n increases in a singular manner. So that is where we are defining that with the orders of a particular polynomial, the order of a particular polynomial, or the degree of a particular polynomial rather, defines the order of execution of time, right? So we will have every polynomial that represents a particular algorithm's time, we can correlate that time with the order of the polynomial. Here what do we write? We have seen here that y equal to mx plus c, and therefore there is no relevance of Tn, there is no relevance of Tn with n, so it does not depend on n. What does it depend on? It depends on nothing. It is a constant time. So can I say therefore it is an order of a constant time? I do not know what time. I will put just 1. 1 represents that constant time. You multiply 1 in a faster machine by some milliseconds. You multiply 1 in a slower machine by some more milliseconds, right? The crux of the matter will be that the line will still remain the same like this, right? So all of them will execute themselves with an order of 1, which means it will not depend on the number of inputs. So what we have established is that an order of a polynomial, or the time taken by a polynomial, is represented as an order, and that order can be order of 1, which is basically meaning that it does not depend on the number of inputs. It remains constant time. The constant time can change machine to machine. That's why I will represent it by a generic word, which is order of 1. And that 1 can be used to multiply and get into the scenarios of various different machines. Can I therefore say that we have also established that time taken can also be represented as an order of n in case the algorithm follows y equal to mx plus c, right? The linear curve of an algorithm, of the time taken by the algorithm, if it can be expressed as y equal to mx plus c, because here we have 1 as the degree of this particular polynomial, hence we can therefore say that this will be order of n. We have also established that we can still write order of n square if we have the time taken by the polynomial represented like this, which is a quadratic equation. So then we can therefore establish that the time taken by a polynomial is typically of two kinds. One, which is constant, where it doesn't follow with any kind of inputs that are given to it. So it doesn't follow with so it doesn't follow with this particular input, neither does it follow with this particular input. I mean, none of these curves changes with the input. So first category of algorithm is this, which is that I'm not going to change if you change the inputs. I will always execute in a constant amount of time. And the second category of an algorithm is this, which says that I'm going to change with the inputs, and I'm going to change with the different asymptotic polynomial equations that I will represent. Sometimes I will represent y equal to mx plus c. Sometimes I will represent y equal to ax square plus bx plus c. Sometimes I can represent some other complexity classes. And we will go through all these classes in this particular lecture. But for now, I think I have established the fact that now you understand that an algorithm has primarily two classes, which is one, which is a constant class, which doesn't change with the time, and another is the class where it changes with time in different manners of asymptotic polynomials, right? But I hope you can understand why we do not call time complexity, never ever call time complexity as the amount of time. That's a wrong definition. Time complexity is not about the amount of time, it is about the order of time, right? Order of time is typically measured by whether you change with the inputs or whether you don't change with the inputs. If you don't change with the inputs, perfectly fine, you are at a constant time, order of 1. If you change with the inputs, then also perfectly fine. Then with inputs n, your time tn will actually change. So with inputs, if your time changes, then what will you achieve? You will achieve either a particular time which is following a particular equation, which could be a linear equation, which could be a polynomial equation, quadratic equation, which could be a cubic equation, which could be a logarithmic equation, doesn't matter. All that matters is it is changing with time in some manner, right? More inputs you give, the more the time taken by the polynomial, and the nature of the curve will be different for different classes of the polynomials, right? So if I just summarize the last 10-15 minutes that we have gone through this, we have established that the time complexity of a polynomial is not the amount of time, point number 1. We have established that the time complexity of an algorithm is defined by the order in which it executes itself as compared to the number of inputs that is given to it. Either it can remain at a constant, which means that no matter how many number of inputs you give, how many number of times you run, it will always execute in a constant amount of time. In that case, we call it as order of 1. We have also established the fact that if in case it changes with the inputs, it changes with the inputs according to some equation, some asymptotic equation, and that asymptotic equation defines the order of that polynomial. So if the equation is y equal to mx plus c, a straight line linear, then the order of the polynomial is order of n. If the equation is order of n square, which is basically if the equation is a quadratic equation, then the order becomes order of n square, and so on and so forth. And we have also explained that how and why an order which is y equal to mx plus c, a curve which is y equal to mx plus c, and another curve which is also following y equal to mx plus c, but with a different slope, can be considered as the same as far as asymptotic equations are concerned. Both of them will execute with order of n, and that is what we have also explained. Now, I think it is time to get into some more examples, and that's what this particular lecture is all about. We will take you through multiple examples, and so that this particular concept is hammered into your concept drawers. So let's take an order of one example here. And this order of one example is very simple to understand. This is basically a simple interest calculation program, and intentionally I have kept the implementation languages different. So I have not mentioned about whether we are defining an int, whether we are defining a float, what kind of language. Yes, we have printf, from where you can deduce that it is probably from a C language, but I'm trying to keep it language agnostic, right? So let us understand what typically will happen from a time complexity standpoint. So if you see this P1, P equal to 1000, you have to ask the question, when you investigate each and every line, you'll have to ask the question, why or how this particular line changes if the number of inputs changes. Does this particular line execute itself in a different amount of time if the number of inputs changes? Here I don't think there is any input here, so we don't have any inputs at all. We are just defining 1000 into P. Every time we run this 1000 into P code, every time it will take the same amount of time. It may take 100 milliseconds in my machine, but every time I run it in my machine, it will take 100 milliseconds. Every time I run this code in my machine, in some other machine, it may take 200 milliseconds. So does it change with the number of inputs? If I increase the number of inputs, it doesn't change. This code doesn't have any inputs, first of all. So it doesn't change with the number of inputs. So I will say that it executes in 1 unit of time. Why unit of time? Because I don't know which machine it will execute. So I will say 1 unit of time. Similarly, this code will take 1 unit of time. This line will take 1 unit of time. It has no relevance with the number of inputs. This line will also execute in 1 unit of time. This printf will also execute in 1 unit of time. So net this executes in 5 units of time. So 5 units of time is what the time taken by the float. Can I write this 5 units of time in the format of y equal to mx plus c? I can write it. I can say the time taken, which is y, which is equal to tn, is equal to c. And in this case, c is equal to 5. So can I say tn is equal to 5? I can say that. And this 5 represents 5 units of time. Can I therefore say y is equal to 0x plus 5? This is what this particular algorithm will follow, isn't it? Because you have 5 as the intercept to the y equal to mx plus c curve, right? And you have 0x as the slope. So aren't we talking about a curve which looks like this? Aren't we talking about a curve which looks like this? What is this? Y equal to 0x plus 5. 0 is the slope of the curve, right? So if we are talking about this, then what is the degree of this polynomial? This is the polynomial, right? What is the degree of this polynomial? The degree of this polynomial is 0. X's degree is 0, right? So if X's degree is 0, I cannot therefore make my order of time influenced on X. So I cannot write order of n for this polynomial because it doesn't depend on n. It doesn't depend on n because n has become 0. The order of the polynomial has become 0. The degree of the polynomial has become 0 rather. And as you see that this y becomes 5 irrespective of whatever value of x you give. It will always become 5, so it is not dependent on x. Hence it is not dependent on n. So this is my tn. Tn is equal to y. And my x is actually the number of inputs. Right? So what will I write? I will write this as constant amount of time. So therefore I will write this as order of 1. It is constant. I do not know that it will take 5 units of time means what? I do not know. I do not know that 5 minutes of work in my machine probably is 500 milliseconds. In your machine, it could be 5 milliseconds. In some other machine, it could be 1 millisecond. I do not know. Right? So I can easily make 5 units of time as 1 unit of time in some other machine. Right? So everything, whether it is 5, whether it is 500, whether it is 5,000, will become translated to an order of 1. Why? Because it does not change with the inputs and it is a constant amount of time for a particular machine. So it is an order of 1. 1 represents the constant amount of time. You multiply 1 with the actual number of milliseconds that is taken, you will get a constant amount of time again. So we represent it as generically as order of 1. So that is how this becomes an order of 1. Now, if we actually investigate into the space complexity, which is the first time we are discussing the space complexities for this particular algorithm, then if you see that space complexity for this curve, for this particular routine, will be like this. Here, we will say that we will take 1 unit of space. P is 1000. Probably we defined it as an integer. Now, an integer can actually take 4 units or 4 bytes in a particular machine. Some other machine may be 8 bytes depending on the compiler. Some other machine integer can be 16 bytes also. We do not know where it is going to be executed. A short integer can be defined as 2 bytes somewhere else. So I do not know how it has been defined, right? I do not know how the machine will interpret the number of bytes for an integer. I know that I have defined it as P equal to 1000 and hence I need 1 unit of space. In space terminology, we represent this 1 unit of space as 1 word, right? So we will say always that we require 1 word of space. If 1 word of space takes 2 bytes, so be it. If 1 word of space takes 8 bytes, so be it. So we need 1 word of space. Here also we need 1 word of space. Here also we need 1 word of space. I do not know that if I defined, of course my algorithm defines it as an integer, but I do not know how many bytes I will get for an integer, which machine it will run. It will define that number of bytes. Which compiler will compile it will define the number of bytes. Which operating system it will run will define the number of bytes. So I will say I need 1 word. You give me whatever is your standard word, I will execute it with that 1 word. Right? So which is where I'm trying to generalize things and saying that I need 1 word of space. 1 word of space. So actually speaking, we should not be doing it in this manner. In time complexities, we will take every statement and put a line and put the time taken. But for space complexity, what we will do is we will find out what are the variables. We will find out that we needed P variable, R variable, T variable and SI variable. These are the only 4 variables that we need for this particular program. So this will take 1 word, this will take 1 word, this will take 1 word, and this will also take 1 word. So this will be total of 4 words of space that we need. Now, do you think that 4 words of space can also be represented as a curve like this? If this is the number of words, right? If this is the number of words and this is the space taken by that number of words, space taken by the number of words, right? Which is also equal to your y. Then what are we saying? Aren't we saying a straight line like this? 4. And we have also established just now that this means y equal to mx plus c, which is represented as your SW, which is equal to your y, is equal to 0x plus 4. Here my m has become 0. That means my slope is 0 and hence it executes itself in a constant amount of time. Right? So that is that constant amount of time, 4. It always will execute with a constant amount of, or it, in fact, it's not constant amount of time, we are discussing space. So it will always execute with a constant amount of space, which is 4. It will always require 4 words, right? No matter however you increase the number of inputs, it will always require 4 words, right? In fact, what we should have done is instead of mentioning this as S of W, because it doesn't change with the space, we should mention it as S of N. And we should mention this as N, as the number of inputs, right? So what am I establishing here? My S of N, which is basically trying to say that do I increase with the number of inputs? I'm saying no, I don't increase. I remain at 4 words every time for any kind of input you give to me. For any kind of input you give to me, I will always remain at 4 words. So this is what it means. We will always be at 4 words of space for any kind of input you give me. So that means that I'm actually executing myself in a constant amount of space. If I'm executing myself in a constant amount of space, then I will write my space complexity as an order of 1 again. As simple as that. So I will write it as an order of 1 again because my space taken is constant as far as this particular algorithm is concerned. It will always take 4 words. No matter however you execute it, how many times you execute it, it will always take 4 words. So with n, your Sn will not change. It will always remain flat. Sometimes you might have a curve like this. Sometimes you might have a curve like this. Doesn't matter. It is still order of 1. This is 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 also order of 1. Right? So this is my axis. Shouldn't put order of 1 here. Yeah. So there you go. So you have an Sn, which is the space complexity as a function of the number of inputs, and it says that I'm not going to change with the number of inputs as far as this example is concerned. So the net result of this particular algorithm is that my time complexity for this algorithm is order of 1. My space complexity of this algorithm is also order of 1. That is the answer to particularly this particular algorithm. Let us go to the next algorithm, which is this. We are investigating now an order of n. We'll do the same way. For this particular, we are investigating time first. So let us do time. This is an array. To actually define this array, I will need a constant amount of time. I will need, let's say, 200 milliseconds, or I will say that I need 1 unit of time. This program will run this particular line always with these whatever 5 elements, 6 elements, whatever is there in this, right? It will always run this. So whatever amount of time is taken to define or get the memory from the compiler for these 5 contiguous elements of the array and put 10, 25, 7, 33 and 15 into that array is 1 unit of time. It will always remain the same every time I run my code in my machine. It will always take that 1 unit of time. It will not increase. It will not decrease. If it runs on some other machine, there also it will take some unit of time, and that unit of time will never change. So I will say it is 1 unit of time. This will take 1 unit of time. This will also take 1 unit of time. Now we are into this for loop. Now let's be careful in this for loop. This I equal to 0 actually executes itself 1 time. When the for loop is about to enter, it will do this initialization, and hence this particular line executes with 1 unit of time. I less than n, how many times does this execute? So if you have n as 3 and you have I as 0, then the first time it enters the loop, it actually checks whether 0 is less than 3. So this is counted as 1 time. The second time it enters the loop, it would have increased I. So I has become 1. It will check as I less than 3. This is the second time it checks for that I less than n. Next time it enters the loop, it is trying to check at 2 is less than 3 because it has I has increased. So this is the third time it checks for that value. Next time I has increased to 3 and it checks for 3 less than 3, and this is the fourth time it checks for that value, and this becomes false, and hence it exits. How many times did it check I less than 3? It checked it 4 times. Right? So what is 4 times? 4 times is whatever is the number of inputs that you have is whatever is the number of inputs that you have. We are actually checking. I said that we have 3 inputs and we are checking for 4 times. That means we are checking for n plus 1 times. Now actually we had 5 inputs, right? Because we have 5 elements in this array, right? So ideally it should have been, this should have gone till 6, right? So we should have checked for 0 is less than 0 is less than 5, 0 is less than 1 is less than 1 is less than 5, 2 is less than 5, 3 is less than 5, 4 is less than 5, 5 is less than 5, and 6 is less than 5. And then it would have come out. And how many times do you think this actually ran? It ran for 6 times, right? The check ran for 6 times, but you had 5 elements. So basically we are talking n plus 1 times. So I less than n is going to execute for n plus 1 times, right? So I'll write like this. Next, you have I++. In I++, that particular line I++, executes itself for n times, right? So when it is 0, after the 0 loop is actually done, it will become 1. Now this 1 with it will enter the next time in the loop, right? So and this 1 will become 2. With 2 it will enter the next time in the loop and it will become 3. With 3 it will enter in the next line of the loop and this will become 4. With 4 it will enter the next time in the loop and this will become 5, right? With 5 it will enter the next time in the loop, and then this 5 is less than 5, right? So this 5 is less than 5 is actually going to make it false, right? And I think in the previous previous example of I less than n, I might have done one iteration larger. I'll go there, but then let me just solve this out for now. 0 to 1, this is the I plus plus. The I plus plus is happening for 1 time. Here the I plus plus is happening for 2 times. Here the I plus plus is happening for 3 times. Here the I plus plus is happening for the 4th time. Here the I plus plus is happening for 5 times, right? So 4 is greater than, it actually becomes 5 in the 5th iteration. Now we have, what have we asked it to do? We have asked the I plus plus to become plus every time the loop is about to, when the loop ends and is about to check the next condition, we have asked it to increment itself. So the first time it increments itself to 1, then 1 is checked with what? 1 is checked with, first time it increments to 1 is checked with 5, right? This is how it gets checked. So this is the first iteration. 2 is checked with 5 next time. This is the second iteration. 3 is checked with 5. This is the third iteration. 4 is checked with 5. This is the 4th iteration. Now 5 is checked with 5, right? So this is my 5th iteration. So basically this last line which returns false is here, right? So that's where what we have established is that this becomes false, and because it becomes false, this will exit the loop, right? But 5, it has increased itself to 5 times, and hence what we are saying is that this particular line will execute itself n number of times, right? So that's what we have written here. This particular line executes itself to n number of times. Now coming back to the previous one, where I think while doing this there might have been some amount of typo in what we tried to do for n plus 1. Let me explain n plus 1 one more time to you. So what we are trying to do is we are trying to see I less than n, how many times it executes itself, right? So we have a value of I as 0. We have a value of comparison with n. Comparison is n with n is happening for 5, right? So this is the first time this comparison happens. So we will take this as iteration number 1. Next time I has increased itself. Now 1 will be compared with 5. So this is your iteration number 2. 2 will be compared with 5. This is your iteration number 3. 3 will be compared with 5. This is your iteration number 4. And 4 will be compared with 5. This is your iteration number 5. And then 5 will be compared with 5. This is your iteration number 6. Right? And here is where it will become false. So how many times have we compared? 6 times. What is 6? This is basically n plus 1. And that's what I have written here. Right, so this is how the middle term actually executes itself 1 count extra, because you have to always assume that a for loop condition check is always executing 1 time extra, because it has to exit also. That is, the false condition is also counted here. Right, so that's on the part of this particular line, how it executes itself. On this particular line, ARR equal to target, this line executes itself for n number of times. It will execute itself for 5 times. However number of times this particular line runs, the same number of times this will run, right? So we know about that. If this is 5, if it goes from 0, 1, 2, 3, 4, this is what it will go to. Every time it will enter the loop. Each and every time it will enter the loop. So how many times it enters the loop? It enters the loop 5 times. So this executes itself n times. This executes itself n times. This executes itself n times. Right? So with that, um, of course, one pinch of salt that you can take is that if this line is not true, if this if is not true, the printf and break will not execute itself, right? So net, you can say, you can eliminate these two and say that one happy path or one critical path, as we so call it, is taking this particular input only n number of times, or this particular line is only executed n number of times. Inside this line may be executed only once, and this line may be executed only once, and it might break. Because you have an if, from a truth perspective, this line will execute, the lines within the if will not execute n number of times, it will execute only one amount of time, because it will match and exit the loop because you have a break there, right? So if this if would not have been there, all these statements would have been executed at n number of times, which is what I had written earlier. Now, overlooking the if I now see that there is a if, then of course the if will execute itself n number of times, but the print will execute itself only one number of times, because once it matches with the if, it will exit. So that's the total amount of time that is taken by this algorithm. So what is the total that we are actually calculating? 1 plus 1 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, 6 plus 1, 7. So 7 plus 2n, or rather 3n. That's the total amount of time that we are calculating. Now, what is this 7 plus 3n? Can we say that this represents this particular graph, where this is my slope, y equal to 3x plus 7. This is my x and this is my y, right? And if I represent it in the form of n instead of x, then can I say that y, or tn, my curve for tn is equal to 3n plus 7. So this is my intercept of 7, right? And can therefore I say that this is equal to my time complexity, and this is equal to order of n, because my largest degree here is 1, right? So I'm saying that therefore this represents the class of polynomials which is linear, which is basically y equal to mx plus c. And for y equal to mx plus c class of polynomials, we know that it is going to be order of x, because the degree of x is going to be 1. So therefore, can I say this polynomial is executing at y equal to mx plus c, and hence order of n? I can of course say that. Now the same thing will go for the space complexities, and if you see the space complexity of this particular graph, you will understand what am I trying to say. So here you will see that this needs n words. The more number of arrays, pockets you will give, the more words it will need from a space standpoint. In fact, let us write the variables that we are going to typically use here. So ARR is the space we will need, n is the space we will need, target is the space we will need, I is the space we will need. That's all we will need. ARR will take n words, right? More number of n's, more number of space. N will take one word. To define n, we need one word, right? Number, that is 5, we need one word. Target, we will need one word. I, we will need one word. Total number of words required is n plus 3. Do you think we can represent n plus 3 as a space curve like this? So this is my 3, and this is my Sn equal to n plus 3. And n is the slope, right, that we have generated out here. So can I say this is in the form of y equal to mx plus c? That is, Tn is equal to n plus 3, where m is equal to 1 and c is equal to 3. We can say that. So basically Tn is following what? In fact, not Tn, my bad, it should have been Sn. So Sn is following what? Sn is following a linear class. Linear class of polynomial. This linear class of polynomial is represented as y equal to mx plus c, right? If it follows a linear class, because it is n plus 3, what is its order? Its order Sn will be order of n, because all linear class polynomials have a degree of 1 and hence order of n. So in this case, the time and space complexity that you will write as a final answer is going to be time complexity is equal to be order of n, space complexity is going to be an order of n also, right? So I hope time and space complexity is becoming clearer as we go forward in this. Let us quickly check this one also. This is a countdown timer and we are not incrementing, we are decrementing n, right? So what happens if we decrement n? How does it change is what I wanted to make you understand, right? So from a time complexity standpoint, let us see this while n greater than 0 will execute itself. Let us say that my n is 3. So at first it will check 3 greater than 0. Then it will check 2 greater than 0. Then it will check then it will check 1 greater than 0. Then it will check 0 greater than 0 and it will come out, right? So 0 greater than 0 will generate a false. So this line executes itself n plus 1 number of times. I hope you can understand that. And inside this will execute n times. This will execute n times, right? So when you enter for 3, this will enter 1 time. For 2, it will enter 2 times. For 1, it will enter 3 times. For 0, this will not enter. So total number of times you get is 3. That is why you will execute for n times each and every statement, right? So this means that the total time complexity is coming to be 3n plus 1. So can I represent 3n plus 1 as y equal to mx plus c? Of course I can, right? Where my m is equal to 3, my n is equal to x, and my c is equal to 1. So I can represent that. So if I can represent y equal to mx plus c, then I know that I can represent the time complexity as an order of 1, because this now belongs to what? This now belongs to a linear class of polynomial. And when it belongs to the linear class of polynomial, the highest degree is always 1. Hence, the time complexity will be 1. Right? I hope you can understand. We have established before mathematics from a graphical standpoint why we said order of n. In fact, this should be order of n. My bad. This is degree 1. Hence, it should be order of n and not n square, n cube, etc. Hence, time the complexity is order of n for a linear class. But we have established that why this is order of n. And why we are neglecting this constant, because this is an intercept to the graph and this is the steepness of the graph. The steepness of the graph can anyway be eliminated by putting it into a faster machine or a slower machine. Hence, it will eventually become an order of n, right? So everything becomes an order of n is what we had established from a graphical standpoint. But from a mathematical standpoint, what I'm trying to say is that an order of n is nothing but the highest degree of the polynomial, which is here x1, right? So we will actually execute this as an order of n and not as n square, n cube, etc. And it is of course dependent on the input, hence n is there. Now that is on this particular while loop. So irrespective of whether loop it goes in the forward direction, backward direction, it will always execute in an order of n. Now one more example if we take, and here we are skipping, making students skip seats and seat during an examination, right? So that they seat in alternate seats, right? So let us take that if we have n taken as, let's say, 10. How does this algorithm behave is what we will want to see. Now this int I equal to 0, will execute itself in 1 unit of time. Now I less than n, and remember that we are doing I plus equal to 2, right? So when value of I is 0, then it is getting compared I less than n. That means it is getting compared 0 is less than 10. This is true. So it will enter and it will do an I plus equal to 2, right? So it will do an I plus equal to 2 means it will become 2. So the value of I with which it will go into the second iteration is going to be 2. Right, so we'll go into the second iteration, or the second iteration with the value of 2. So now 2 will be compared with 10. That will also be true, and I will be incremented to 4. Now 4 is what we will enter the third time. So this will become 4 is less than 10, and this will become 6. With 6 I will enter, it will become 6 less than 10, and this will become 8. With 8 I will enter, and I will check 8 less than 10, and I will make it as 10 after increment. With 10 I will enter, I will check 10 less than 10, and this will not go further. How many times did I check? I checked it 6 times. So this I less than n is getting checked 6 times. What is that? That again is n by 2 plus 1. Right? 6 times is n by 2, which is 10 by 5. 10 by 2 is equal to 5 plus 1. And how many times this I plus equal to 1 is executing? This is done. This is what we are seeing now, I plus equal to 2. This is executing 5 times. So this is executing for how many times? This is executing for n by 2 times. Right? So this is what is happening. This is what is happening here. So I less than n is getting executed n by 2 plus 1 time, and this is getting executed n by 2 times. And within each of these for loop statements, we will execute ourselves n by 2 times. Right? The number of times it increments or decrements is the same number of times it will execute the loop. Right? So we will execute the loop n by 2 times. So we need that amount of time. Each time means some amount of milliseconds. So we'll need that amount of time. So what is the total amount of time we need? So let us put it as the equation 1 plus n by 2 plus n by 2 plus n by 2. So this becomes 2 plus 3n by 2. Can I say that this is nothing but this? Can I say this is a slope of, this is an intercept of 2 and a slope of 3 by 2? Right? Can I say this is my time complexity, where this becomes y equal to mx plus c? What is m here? M is 3 by 2, x is equal to n, and c is equal to 2. So does this follow a linear class? This also follows a linear class. So can I say that this linear class time complexity is order of n again? Why? Because the power of this particular n is 1, which is why I'm saying order of n. 3 by 2 is just a coefficient defining the slope. So slope, as I said, can be nullified by a fast or a smooth machine. And likewise the intercept. Doesn't matter from where you start. Right? So that's how we are calculating the time complexity of this, also to be as order of n. Right? Now if I see what is the space complexity for this, right? I have defined how many variables are required. We have defined I, we should have defined n, and we have an ARR. So I takes one word, n takes one word, ARR takes n words. So this is n plus 2, and n plus 2 is also y equal to mx plus c, where Tn is equal to n plus 2 is equal to, which implies that m is equal to n, which implies m is equal to 1, n is equal to x, and c is equal to 2. And therefore I can write this as, this should have been space complexity because we are talking space here. Therefore I can write this as Sn with n will follow something which is like this, n plus 2. And this is a linear class. This is following a linear class of polynomial. And because it is following a linear class of polynomial, I can say my space complexity is an order of n, because the degree of a linear class is always 1. So that space complexity is therefore order of n. So that's on the order of n for the seating arrangements. Now let's make it a bit more advanced now by bringing in two loops. Suppose we want to pair each student with each other, right? So each student is supposed to be paired with each other, and we will say that how many pairs are we going to generate then. So this is the code for that. If you see here, I moves from 0 to n, and here also I moves from 0 to n. Now come back to the previous problem. Okay, in the previous problem, in fact, I think we have removed the solutions for the previous problem, but no worries, we will do it here. Now we will just try to establish one thing. How much time does this take? How much time does this entire thing take is what we will try to establish, right? So, and this we will continue doing in all our future examples, right? So we will try to establish now how much time this particular line takes, and we have established it before also. Int I equal to 0, this takes how much time? This takes 1 unit of time. I less than n takes how much time? It takes n plus 1 unit of time. And I plus plus takes how much unit of time? It takes n unit of time. So total time taken is 2n plus 2. Now can I say that 2n plus 2 is the same as n units of time? Can't I say that? Of course I can say that, because 2n plus 2 is a curve like this. Can I not show this curve like this, which is our n? Can I not say that from an asymptotic standpoint these two curves are the same? Because it only depends on n, nothing else but n. So this curve, if I run it on a faster machine, may become equal to n. So can I not say this curve is just looking like this? This curve is the same as this curve when it runs on a faster machine. It takes 2n amount of time on a slower machine, but it might take n amount of time on a faster machine. Both these curves are linear classes, hence their degree is 1. Hence they will always execute in an order of n. That means more n you give, the more the time will actually increase. More n you give, more the time will increase. Can I not say that? Both of them have the same characteristic, both of them have the same behavior, both of them will increase in the same manner if you give n. One will increase faster, one will increase slower, but that depends on the machine. If I change the machine, both might execute with the same order of n. So I will say that 2n plus 2 is nothing but n. Because from an asymptotic standpoint, all that matters is that it executes in what order? This executes in order of n. 3n plus 2000 is also an order of n. 200n plus 5000 is also an order of n. All of these can be translated into an order of n kind of a graph because they change with the number of inputs. The slopes here have no significance. Because that depends on the performance of the machine. If the performance of the machine increases, decreases, these slopes might become unity. And hence it will go towards becoming n. All of these will go towards becoming n depending on the machine. Hence, can I say that all of these depend just on n, right? We will say that more it increases, more n increases, more the time complexity will increase. And hence we are not bothered about the magnitude in which it increases, the steepness in which it increases, the slope in which it increases. We are just worried about the behavior of the increase. Is it going to increase in a linear fashion? If so, it is going to be order of n, order of n, order of n. Everything will become order of n. And that's what we had proved earlier, that's what we are proving now, and that's why we are saying that the degree of the polynomial is still 1. Degree of the polynomial is still 1 here. Right? So we are going to have a degree here 1, degree here 1, and hence it is always going to be an order of n from an asymptotic execution standpoint. So if we have established that, let us remember this going forward, that for all loops, for the for condition, we are going to write an order of n. Right? So we will say that this line executes in an order of n. This line, if this line executes in an order of n, then all the inside lines, all these lines will execute in an order of n, isn't it? Every line within the for loop will run n number of times because this line itself runs n number of times. So now if we come inside, we have another for loop. So this for loop also executes itself in an order of n. And all lines inside this for loop, this line and this line, will also execute in an order of n. Right? So let me repeat one more time. This is where, in this style of frequency counting, is what we will actually go forward as we go forward analyzing all asymptotic complexities. So this line, as we established, is an order of n. Every line inside this for loop will execute therefore with an order of n. Now, this line also executes, because it's a for loop, it also executes in an order of n. Right? So every time this outside loop enters, n times it enters, every time this inside loop executes for n times. That's why there is a multiplication sign. Now consider the inner loop. This inner loop, these two syntaxes will execute the order of n times, because the outside loop executes, this particular second loop actually executes n times. So every line inside will also execute n times. Right? So what did we achieve as the total order? We achieved the total order as n square plus n square plus n square plus n. So this is nothing but 3n square plus n. Now, and can we say that this is looking like ax square plus bx plus c, which is what? A quadratic equation. So now we are changing our class, right? So quadratic polynomial. So this is a new class that we are now seeing. So what is x? X is equal to n. What is 3? A equal to 3. Right? And what is b? B is equal to 1, because you don't have anything with n. What is c? C is equal to 0. So that is how you have defined y equal to ax plus ax square bx plus c as 3n square plus n. So this 3n square plus n represents a quadratic polynomial in the same format, universal format, as y equal to ax square plus bx plus c. And this is looking like, it's going to look like this from a graph standpoint. Right? Here you will have your intercept c, and then you will have the graph which is mimicking ax square plus bx plus c. So this will be your time complexity, this will be your n, right? And you will have a curve which is looking like this. So any class of polynomial that follows this curve will always have what? The order as the highest degree, of the quadratic polynomial. The quadratic polynomial highest degree is this, which is 2. So it will be order of n square. Right? So that is how you arrive at the time complexity for this particular algorithm, which is order of n square, from a perspective of what you see on the curve, what you see on the quadratic polynomial alignment. Now it is very easy to imagine it in one shot. If you see a loop, it's always going to be order of n. And if you see two loops which are nested amongst each other, right? If you see a loop, it's always going to be order of n execution. And if you see a nesting here, right, then this is also going to be an order of n. So this should be a multiplication of both, and hence order of n square will be your order of n square, which is the time complexity of this particular problem. Right? So that's typically how this thing will go. Right? So this is how we will talk about this. Now what about the space complexities here? Right? Can we establish some space complexity here? How many variables are we defining? We are defining I, which requires one word. Why? Because it will only execute one time. The definition of I will only take place one time. How about j? The definition of j will take place n number of times. So I need n words for that. Because this int j equal to 0 will be fired every time this loop enters. And this loop enters n number of times. Right? So j will be fired every time this loop enters, and hence j equal to nw. So your total number of words required is n plus 1. And n plus 1 is equal to y equal to mx plus c. This will give you an order of 1. So the space complexity will be an order of 1. The time complexity will be an order of n square. So as I said, if you see two loops, right? Of course, if they are nested two loops, and if they go till n and they are incremented in a linear manner, it will always be an order of n square. However, if you see only one loop like this, right, and this is going till n, right, and if you see that it is going, in fact, if you see that it is going till n and it is incremented in a linear manner, right, we will always consider this as order of n. One single loop. So just by seeing the code, you can say whether it is an order of n square. One single loop means order of n. Without any loop, if you see any code, it is going to be an order of 1. There is no loop, right? With the loop here, it's going to be an order of n because we have a loop here. Forget about all the constants. Order of 1 will always become negligible as compared to order of n, because your highest degree will still be order of n. Because you have a single loop here, this is going to be an order of n. And we established here also, this is a loop here, so it's going to be order of n. There are no further loops, only one n. Here also we established this is going to be order of n. There is one single loop. Here there are two loops, one within the other, so it's going to be order of n square. But remember, be careful that these two should go till n and it should be in a linear manner. And we'll see that when we go into the logarithmic. Why am I saying this? Let's see this. This is going to be interesting. Now this executes itself n times. We all know, but we don't know how many times this will execute. Why? Because this goes till I, and I changes every time. How many times will this execute? We do not know. Right? So this we are struggling. Now we have to therefore do a dry run of this, a trace of this in order to get to the order. I hope you can understand. Again, I'll repeat. We know this takes n times, but we don't know how many times this takes. So I can definitely write that this line will take n times. And because all these lines are inside it, this will also take n times. This will also take n times. But this line will take how much time to execute? We do not know. So the multiplication that I have to do here, I do not know. The multiplication I have to do here, I do not know. And hence I'll have to do my trace. Hence I will have to do my dry run. So that is what I'm trying to do now. So what I'll do is I'll say that with I, and I will say with j. And let's say we have taken a 3 by 3 matrix. Right? So we are trying to sum the diagonal elements of a matrix. We have taken a 3 by 3 matrix, and hence your n is equal to 3. The value of I is 0. I is compared with n. Right? So I is compared with 3. So 0 is less than 3 is true. It will enter. And inside j is 0. And j is compared with I. So j is compared with 0. And when j is compared with 0, it doesn't enter. Now j increments. When j increments, j becomes 1. In fact, 0 less than 0 itself is going to exit the loop. Right? So incrementing j is not needed. So this itself will exit the loop of the inner loop. It will come to the outer loop now. The outer loop I will increase. 1 is less than 3 will become true. J will again start from 0. And when j starts from 0, 0 will be compared with 1. This is going to be true. So this will execute one time. Right? Now, next time what will happen is, for the same set I equal to 1 in the same order, right? When j is incrementing, j will become 1 less than 1. Right? So for the same inner loop, I'll not write here 1 because it might confuse, because this 1 is already static now. It is running the outer loop at 1. Inner loop is changing from 0 to 1 to 2 to 3, etc. 1 less than 1 becomes false, it exits. So what did we achieve? We achieved one more iteration. Because the inner loop exits, the outer loop increments. The outer loop checks itself with 3. J's value again starts from 0. And that 0 is again getting compared with 1. This executes. J becomes 1. 1, I'm sorry, this should be 2 because my I has become 2 now. So this gets compared with 2, this gets executed one time. Next we have 2. 2 is getting compared with 2, this does not execute. So do we see that the number of times I is, that many number of times the inner loop runs. So can we say that inner loop runs n times for I equal to n? We can definitely say that. So can I say therefore for 3, this would run 3 times? Can I say for n, it will run n times? For a value of I equal to n, it will run n times. Right? I think I have established that amply clear here, and which means that the number of times that I have executing or I am executing this particular loop is basically this one plus this 2 times plus this 3 times plus this n times. So 1 plus 2. So the number of times I'm executing it is 1 plus 2 plus 3 plus 4 plus n times. Can I say therefore the number of times is an arithmetic progression which translates to this? So therefore can I say my time complexity is this? So my time complexity is coming to be Tn equal to n into n plus 1 by 2. I hope you understand. I'll repeat again that every time I increases, j runs for that many number of times. Every time I increases to 2, j runs for only that many number of times. 2 means 2 times j will run. 3 means 3 times j will run. N means n times j will run. So can I therefore say it runs these many number of times? And therefore can I say by AP logic, my formula for Tn is this. If my formula for Tn is this, then what does this translate to? Can I say that this is n square plus 1 by 2, which can be represented as half n square plus half? Can I not say that this is equal to ax square plus bx plus c? I can say that. So what class of polynomial does this fall again under? This falls under the quadratic class of polynomial. And for a quadratic class of polynomial, the highest degree is 2. So therefore, this will be an order of n square. So this also is an order of n square as far as time complexity is concerned. Now going forward, I'll not discuss about the space complexity. It will be easy for you to find out the space complexity. In this case, the space complexity is supposed to be n square again, right? So I hope you can figure it out, because your matrix itself is an n square complexity. In fact, let me do it quickly, but going forward, we will try to skip the space complexity. It's going to be a simple calculation just for the from the interest of time. You can always put in a comment and ask me if you are not sure about the space complexity. So what is going to be the space complexity here? Let us calculate. What are the variables we have taken? We have taken I, we have taken j, and we have taken matrix. Now I will be defined only once, so I need one word for I. J will be defined I times, and I will go until n. So I will go until n means j will be defined n times. So I need n words space for j. Right? Next time I would need this summation in terms of the number of matrix. So sum will be needed also as a variable. So the sum will require one word. It's just a variable. Matrix itself is I cross j, and I cross j will require n square amount of space. So I need n square amount of words. So what is the total number of words I need? I need n square plus n plus 2, which is again falling under a quadratic class of polynomial, which means that I'm talking about a space complexity of the order of n square. Why? Because this is the highest degree of the polynomial, and hence we should take an order of n square as the space required for this particular polynomial. So that's typically on the order of n square. Now we'll take a break, but then let's do this n cube and then we'll take a break. From a for loop standpoint, if I do a matrix multiplication, this is typically the matrix multiplication problem that you would have completed in your earlier semesters, earlier classes. And that's what we are trying to explain here. From a complexity standpoint, what would it have been? So let us quickly calculate the complexities here. This particular line, as you know, is a for loop. It will execute itself for n times. This particular, all the items within this for loop, because of this n, will also execute n number of times. Now this line is also a for loop by itself. Because it is a for loop by itself, it will execute itself for n number of times. All the lines inside this for loop will execute itself n times because this is n. Now don't forget that you have one more loop, and that one more loop that you have is going to execute itself n times. Right? And inside that one more loop, whatever number of items are there will execute itself n times. So what do you have? You have these many number of summations to actually probably do. So you have an n cube plus n cube plus n square plus n. This is what you have. So you have 2n cube plus n square plus n as the time complexity asymptotic polynomial for this. Isn't it looking like ax cube plus bx square plus cx plus d? And this is what we are calling as a cubic polynomial. So we are now into a different class of polynomial which we call as a cubic polynomial. And this cubic polynomial executes itself in this particular order, and therefore the degree of this polynomial, as we can see, the highest degree is 3. So for all cubic polynomials, can we say my order of n is equal to, and can we say that my time complexity is equal to order of n cube? Because my highest degree is 3. So that is what when we mean by order of cubic polynomial, this is where the order of 3 or n cube is actually coming up. Degree 3 and order of n cube is actually coming out of. Right? So with that, we have established various facts. We have understood what is time complexities. We have understood why order of 1, why order of n. We have taken examples of order of n square. We have taken examples of order of n cube. Now we will do these last 3 after a break, and then we will close off the session with classes of functions. Let's meet on the other side of the break. Hello, welcome back. We have finished off with most of the time complexities that are critical, and we are right now starting a couple of them which definitely are critical, but will fall under a different class of time complexities. We have covered constant time complexity, we have covered linear time complexity, we have covered the quadratic and the cubic time complexity. We are now investigating the logarithmic time complexity. So this problem here is to double money every day, right? If that is the problem and we are doing this code in this manner, then let us see how we can calculate the time complexities. We have to be very careful when we are comparing time complexities on these two things. One, what are you comparing against? And two, how many times or how is the increment happening? So if we see this particular statements, can we say for sure that this will execute itself n number of times? We can't, because the value here does not grow by 1. The value here grows by a multiple of 2. So how many times this loop will run, we do not know. We cannot say it will run n times. We'll have to calculate how many times it runs, right? So that's what we will try to do now. So let's try to calculate how many times this loop runs. Let's see that. Let's put a count here. Let's put a value here, and let's put value getting compared with n, and let's put the value incrementing to a multiple of 2. Let us try to figure out if we can run this on a dry run and see if we can generate out a pattern. The first time this particular algorithm runs, the value is 1. And this value is less than n. Let's take n as a large number. Let's take n as 100, right? So we have 1 is less than n. That is true. So this is true. So if this is true, then this loop will actually run and value will eventually become 2. Now, if that is the case, the next time this loop runs, that is the second time this loop runs, it will start with 2 because you have already changed the value to 2. 2 will be compared with 100, which is also true. And this will mean that 2 will be again multiplied by 2. Next time the loop runs, the value is already 4, right? And then 4 is getting compared with 100. And this is also true. So this means that this loop will run 2 multiplied by 2, which is 4 multiplied by 1 more 2, right? Next time the loop runs, it is 4. The value is the value is 8. And 8 is less than 100 is true. And therefore this loop will run 2 multiplied by 2 multiplied by 2 multiplied by 2. So this is coming from the previous step, like this came from the previous step, etc., etc. Right? So net, we should do it like this, yeah. Net, if we can create a general formula out of this, can we say this represents 2 to the power 1? Can we say this represents 2 to the power 2? Can we represent this represents 2 to the power 3? And this represents 2 to the power 4. If we can do that, then do we know how many times it will run? What is this count going to be? How many times will this run? This will run till this value is less than n. But what will be this value? We do not know. Where will this value stop? We do not know. Or if at all it stops somewhere, how many counts will it achieve? If it stops somewhere means it will be less than 100, just less than 100. At that time, what will be the value of 4? We do not know that, right? So what we will say is, if this goes on like this, do we see a correlation? Do we see a correlation of this number with this number? We definitely see a correlation. That the number of times it is running is equal to the number of power that we see in this value, right? So that's what we will take an advantage of. And therefore we will say that if this runs k number of times, I do not know whether k has crossed n or not, right? So I do not know whether k will cross 1000 or not, or 100 or not. And I'll say that if it runs k number of times, then that k is going to be definitely less than 100. And that k will produce 2 to the power k as my value of value, right? As the outcome of value. So can I say that if the algorithm, if the count, if it runs for the kth iteration, the value of value will be 2 to the power k, right? So with that, we will hold our thoughts there, and we will assume that at the kth iteration, I will have the value as 2 to the power k. Now, if you see this, when does it stop? Value is less than equal to n, or less than n is for our entry point, right? We will enter when this is true. So can I say that value is greater than equal to n is our exit point? That is where it will stop. And what is the value? The value is 2 to the power k at any point in time. So can I say 2 to the power k is greater than equal to n will be the exit point? And if I can say that, can I simplify this by saying that instead of greater than equal to n, when it becomes equal to n, then it will exit? I say that, I can of course say that. And 2 to the power k equal to n means what? 2 to the power k equal to n means that we are looking at k as log base 2 of n. Why? Because 2 to the power, let's say 3 is 8, right? Which means that log base 2 of 8 is equal to 3, right? So this is what from a logarithmic standpoint, I'm sure all of you know that the power of 2 is basically the answer that you get when you put the log to the base 2 of the outcome, right? So that's why k log base 2 to the power k equal to n would mean that k is equal to log base 2 of n. And what is k? The number of times. K, see, this is what was k. So k was the number of times. So number of times that this loop will run will be log base 2 of n. I'm sure you can understand now where I'm going, right? So let us conclude that this particular algorithm or this particular line will run log base 2n number of times, right? So if I just write the order of this time complexity for this particular problem, of course you will have order of 1 coming out of here, order of 1 coming out of here, which will be negligible when compared to log base 2 of n, because we are with the time complexity function which will fall under the logarithmic class. So this particular example, this particular for loop, we have proven that it will execute at log base 2n number of times, right? So we have proven that k is equal to log base 2 of n, which would mean that this will run the count of times it will run, because k is the count of times it runs, is equal to log base 2 of n. And because it runs log base 2 of n, we can therefore conclude it belongs to the logarithmic class. And because it belongs to the logarithmic class, every logarithmic class should execute itself typically of the order of log base 2 of n. Therefore, the time complexity for this particular function will be log base 2 of n. So that's on the time complexity of this particular problem. But then there is a catch here. There's a small catch here. The small catch is that log doesn't always give you a whole number, right? And I'll explain what I mean by that. If I say that my n is 8, right? So what can my values be? If my n is 8, my value can be equal to 1, because 1 in that case will be less than n, which is basically less than 8. So my value, this will be true. This will run for 1 time. So this is 1 time it will run. When the value will become 2, because we are multiplying here by 2, right? So when the value becomes 2, it is also less than 8. So this is also true. And this makes it run the second time. Next time the value will become 4, and this is less than 8. This is also true, and this will make it run the third time. Next time the value will become 8. 8 less than 8 is false, and this therefore will not run the fourth time. How many times have we run this? We have run this 3 times. And how did we get this 3? We got this 3 because our n was 8, right? And we have just now proven the time complexity is log base 2 of n. So log base 2 of 8 is equal to 3, and that 3 is what we have here. That 3 is what we have here, right, as the number of times it runs. So as you can see from the formula, we can easily calculate the number of times it runs, 3 times. But if you put n is equal to 10, 12, etc., whatever number you want to put, then how does it look? The first time it will be 1 less than 8. This will be true, and it will run once. The second time it will be 1, 2 less than 8. This will also be true. It will run 2 times. Less than 8. This is also true, and it will run 3 times. This time it is 4 less than 8. This is also true. It will run 4 times. And the fifth time it will be 8 less than 8, and this will be here I did 3 less than 8. It should not be there. So we should say 4 less than 8. This is true. This third time that it runs 8 less than 8, and that is in fact all of this was with n equal to 10. So my bad again, I should have put 10 here. So this will be also true, and this will be 4 time, and then 10. 8 will become 16, and 16 less than 10 is false, and this will not execute. How many times did we run? We ran it for 4 times. So we ran it for 4 times, but when we put it in the formula, what do we see? Log base 2 of 10 is equal to what? Right? So I do not know what log base 2 of n equal to what, because this is not going to be a perfect 2 to the power something will not give me 10. So 2 to the power something will give me 10. That something is what we are trying to find out. And that something, if you calculate, it will be 3.32, right? So basically what we are saying is log base 2 of 10 is 3.32, right? So if this is 3.32, it says that the total number of times with n equal to 10 it will run is 3.9. We say whatever log will give you, do not take that number blindly as the number of times. Take the ceiling of that number. So the ceiling of 3.32 is equal to 4. Right? I hope you are aware of this. Ceiling of 3.32 is 4. Ceiling of 0.6 is 1, and so on and so forth. So that is why if you see what I have given here is the ceiling of log base 2 of n as the order. So be careful when you are talking log base 2 of n, it is not just log base 2 of n, it is the ceiling of log base 2 of n as the order of the complexity that you will get. So I think that is understandable, and that therefore let's move on to the next complexity example. This is also a log base 2 of n, but instead of multiplying things by 2 times, we are dividing things by 2 times. Right, and that's where I said be careful whenever you see things which are relevant from our influencing the complexity class. Those 2 things are what is your comparison and what is your increment decrement. If they are not putting a linear angle of increment decrement, then rest sure that you are going to not get an order of n or an order of n square or an order of n cube. You will be looking at complexity classes of exponential complexity classes, logarithmic complexity classes, root over complexity classes, and classes like that. We are discussing logarithmic now, right? So let's try to solve this now, right? So what do we have? We are basically halving a piece every time the loop runs. We have taken some pieces and we are taking a half of the count of those pieces every time, right? So that's what 100 we have taken as the pieces, and we are reducing those pieces by half every time. So what does that mean? It means that we started off with n. Our first time we entered, it was n. Now second time we are entering, this n has become n by 2. Third time we are entering, this n has become n by 2 square. Right? So this way, what is happening is, let me put it in a different way so that you can understand in the normal dry run fashion, right? So let us say that we have a count of run, we have our pieces, and we have the comparison of the pieces, right? So pieces is getting compared with 1, and then we are incrementing or decrementing pieces by slash equal to 2. So in the first time it runs, the pieces is having a value of n, right? Let us say the pieces has a value of n. In this case, n is 100, right? So n is greater than 1 is true, right? And then pieces will become n by 2. In the second run, pieces starts with n by 2, and n by 2 is greater than 1. So this is also true. And then this n by 2 will become n by 2 square because we are halving it. In the third time it runs, we have started with n by 2 square, and n by 2 square is greater than 1, which is true. And therefore we have n by 2 cube as the next time it halves it. So do you see a correlation again with this 1 and this n? With this 1 and with this denominator, where you have 2 to the power 1, you have 2 to the power 2, and you have 2 to the power 3, right? I'm sure you can see that. Now, if that is the thing that you see, right, what on the screen, that your number of times this gets executed, or the outcome that pieces will have, is dependent on the number of times. Can I say, therefore, in fact, we should have started by saying that we typically do not know how many times this loop will run, because pieces is getting halved every time. I do not know how many times this loop will run, hence I will do this dry run. I have found that my count is dependent, or the count influences the value of pieces, right? And if I therefore say that I am at the kth count, then my pieces would have a value of n by 2 to the power of k. And if you see, the value of pieces greater than equal to 1 is when you are actually running the loop. So can I say the loop will stop in the opposite direction, that is pieces is less than equal to 1 will stop the loop. And the value of pieces is n by 2 to the power k for the kth iteration. So can I substitute this here, n by 2 to the power k, and can I say is less than equal to 1 is when it will stop? Can I therefore say that n by 2 to the power k is equal to 1, which implies that n by 2 to the power k, which implies that n is equal to 2 to the power of k? Why did I take equal to? Because when it becomes equal to, at that point the boundary condition starts and it will slowly start falling behind, and it will stop immediately at n equal to 1, right? So the equal to part of 1 is the starting point of it stopping. So once it has stopped, there's no point going behind on the equal to front. So we have taken it as equal to is the point when it stops. So it stops when n equal to 2k. What does this mean? This means again that k is equal to log base 2 of n. So are we talking about the complexity, logarithmic complexity class? So we are talking of the logarithmic complexity class here, and whose complexity is therefore the order of log base 2 of n. So that's what we are talking about here. Now, if you can understand this, then definitely you will be able to understand this particular puzzle, which is more to do with two logarithmic numbers coming in. So if you see this, we are talking about a population double, and then we are basically randomly logging entries of what the population is on the second loop. So first loop is doubling the population and logging the entries, and the second loop is randomly checking each logged entry. So what we are trying to now establish is that we know that with a star equal to 2 kind of a concept, where it increases by a multiple of 2, right? You saw this here. With a star equal to 2, you are getting a complexity of log base 2, right? So you are getting a complexity of order of log base 2 of n when you had the value increasing by star equal to 2. So can I therefore say that this particular loop will have a complexity of log base 2 of n? What is n here? N is your max population. So I'm assuming my max population is equal to n, right? So this is my max population. So can I therefore say, because it is star equal to 2, I will say that this particular entry executes itself for log base 2 of n. This particular for loop, if we come to here, will execute itself for log base 2 of n also. And in this case, the log base, why? Because of course you have the same thing here, which is star equal to 2. But what is happening here? The special thing that is happening here is that it is dependent on log entries. And log entries is what you are getting here. So this particular line is executing itself log base 2 times of n. Right? So if my log entries is log base 2 of n, then if I write that this particular second loop is also going to execute itself for log base 2 of log entries, can I substitute that previously? Because log entries is actually going to execute for log base 2 of n times, because the outer loop is executing for log base 2 of n. So log entries will execute itself for log base 2 of n times. So can I therefore write this as log base 2 of log base 2 of n? So which means that this is log base 2 of n, and this n actually stands for your max population, right? So this entry, which is log base 2 of n, is the time complexity for this particular for loop. How about the time complexity of the previous for loop, right? In fact, if you see, if I take this from a clean slate standpoint, you would understand that intentionally I had omitted the scalar quantities. I'll bring back the scalar quantities for you from a perfect understanding standpoint, and then we can debate on what can be the complexity. So we are saying n is equal to max population. So hold that thought. When that n is equal to max population, we have established that this will execute itself for log base 2 of n, which means everything within it will execute itself for log base 2 of n, which means the total time complexity of this particular for loop will be 2 log base 2 of n. And we have already established previously that 2 log base 2 of n, we can eliminate this because this only influences the magnitude of the time complexity, which we can of course change by changing the power of the machine. So can we therefore eliminate this 2 log base 2 of n and say that what we have is actually log base 2 of n as the time complexity. So then that means that log entries executes itself log base 2 of n times. So if I put log entries here, then this is also going to execute itself for log base 2 of n times. But we have this as a log. This check star equal to 2 means that this entire for loop will execute itself for log base 2 times. So what log base 2? Log base 2 of log entries. So log base 2 of log entries time. But we already know log entries executes itself for log base 2 of n times. This we already know. So can we therefore write log base 2 of log base 2 of n? Right? So of course we can write. So then what happens is we can therefore write this particular line executes itself for log base 2 of log base 2 of n times. And all the lines within it execute with the same log, which is log base 2 of log base 2 of n. So what we have here is 2 log base 2 of n, right? 2 log base 2 of log base 2 of n, which actually we can again with the same argument say as log base 2 of log base 2 of n, right? So now we have something which is log base 2 of n and something which is log base 2 of log base 2 of n, right? If you add them up, so log base 2 of n plus log base 2 of log base 2 of n will add them up to log base 2 of n, because that will be the higher power that we will be taking. So this is your time complexity for this particular problem. So we have established that the time complexity for this particular problem is log base 2 of n. And this is how we calculated it. Now if we go on for one more logarithmic problem, I think this is the last logarithmic class problem. So this particular line is going to go on till n with the increment of linear increment. We know this takes an order of n. This goes on till n, and this takes days star equal to 2. We have seen that this has to be okay. Before we go there, let us do this thing. Let us say that this particular first line executes for n times, hence all the inner lines will execute for n times. Right? Now we will say that okay, this is also a loop. We also have a loop here, and this loop has days star equal to 2, which means this loop will take log base 2 of n times. Everything inside that loop will also get completed in log base 2 of n times. So what do we have in terms of the total time complexity now? The total time complexity now therefore adds up to 2n log base 2 of n plus n. That's what it adds up to, right? Which is where we will say again, this particular line is only the magnitude. We can neglect this magnitude because it depends on the machine power, and hence we have n log base 2 of n plus n. And this will be the higher degree, and hence our time complexity will be n log base 2 of n. So that is the answer to this problem. I hope you can now resonate how we can quickly calculate time complexity and put it against a complexity class. The last type of time complexity that we will discuss for this is the root over of n. And if you see, I've written a code which is basically reading one page every day. Now, if you see carefully, this particular line, pages less than equal to n, is the condition of exit. Do you therefore know how many times this will execute? You don't know, because you are increasing I on this side, but your pages is getting increased with the concept of I. So I in one hand is increasing, page on other hand is dependent on I, and hence you will terminate at pages less than equal to n. You do not know how many times it will execute. And when you do not know how many times it will execute, it will either be a logarithmic, exponential, or a root over. And that's what we are trying to establish here, how to see what kind of time complexity are we talking about here. So what do we have here? Let us do a count again. Let us do I. Let us do pages less than equal to n. Let us do I plus plus, and let us do pages plus equal to I from a dry run perspective. So let's say I'm entering first. My I's value is 1. Pages value is 0. So 0 is less than equal to n. That will be true. Right? And I plus plus. First of all, what will happen is not I plus plus. So first of all, our pages plus equal to I will happen. If you are aware of how C works, that's what it will happen. So first of all, pages plus equal to I will happen, and then your I plus plus will happen. So your pages plus equal to I will actually go from where to where? Let us see that. So pages plus equal to I. So pages is what? 0. I is what? 1. So 0 plus 1. What will I plus plus become? 2. Next time we run, I is 2. 2 is, and our pages is actually 1. 1 is less than equal to n. That is true. So the pages now increments itself by I. So we already have 0 plus 1. So we'll increment it by I. I's value is 2. I will become 3. So it will enter the third iteration with I's value of 3. And the pages here will be compared, which is right now at 3, will be compared with n. And then pages will increment by 0 plus 1 plus 2 plus the value of I, which is 3. And I will become 4. And in this way it will go on. Can you see a correlation between I and the last number here? You can see a correlation between I and the last number here. Right? So can I write, therefore, that at the kth time, at the kth iteration, when I's value is k less than equal to n will be true. And I get just dot k as the value. Can I see when it will stop? It will stop when pages is greater than n. What is the value of pages? The value of pages is this. What is this? This is again an AP. Can I say this is equal to n into n plus 1 by 2? So can I say n into n plus 1 by 2 is greater than is my termination condition? Therefore, can I say that n into n plus 1 by 2? If I just put equal to just from a inequality to equality equation translation, then can I say this? Of course, I can say this. Just after this, it will stop, is what I'm saying. Greater than means just after this equal to, it will stop. So can I say that it is n into n plus 1 is equal to 2n? Right? And for all practical purposes, can I therefore neglect the other powers and say n square is equal to 2? I'm sorry, this will be 2n, not to the power of n. So can I therefore say that n square is equal to 2 times of n? We can of course say that, right? So net, what is happening here? The amount of time we are going to take here will definitely therefore be a fact. If we had to take, because we had taken n here, we should not have taken n here. We should have taken it as the arbitrary count, right? I overlooked this and made it as n because of the arithmetic progression. I should have kept it as k into k plus 1 by 2, right? So that's why we were getting n on both the sides. So if we actually correct that mistake, then we can actually say that this is equal to k into k plus 1 by 2. And if that is k into k plus 1 by 2, then my condition is pages is less greater than equal to n, and pages is k into k minus 1 by 2. So this k into k plus 1 by 2, rest of the things will remain the same as I did it, right? It will be greater than n. And I can therefore put k square, or rather I'll keep it at k, and I will say that k into k plus 1 is equal to 2n. Equal to why? Because I'm eliminating greater than just from an inequality complexity standpoint, and I'm saying just after this equal to, it will stop, right? So therefore, can I say k square equal to n after neglecting this constant and after neglecting this constant? So approximately I will say that k square is equal to n, which means that k is equal to root over of n. So when will it stop? It will stop just after k is equal to root over of n. So what is the time complexity of this particular? It's a square root class problem, and the time complexity of this is root over of n. So that is what or how we have derived that the time complexity of this problem will be root over of n. So net what you need to do whenever you see equations where or problems where you are actually struggling to find out the time complexity because you do not know how many times this will run, either because this is not plus plus, this is plus equal to 2, or slash equal to 2, or star equal to 2, and this may not be directly correlated with n because now we see a dependency on I. So all of this is complicating things of us to judge how many times this will run. Then do a dry run like this. In the dry run, try to find a correlation between the iteration and the number of times it is actually running. Now stop it at an arbitrary iteration, which is k, and try to figure out the correlated formula. From that correlated formula, create the general formula, and that general formula put it in the exit condition, right? And that exit condition then solve. Then you'll get the value of k, and k was the arbitrary count where you stopped. So k will actually stop when you are actually exceeding the condition that is there in this loop. So you will get a value of k, and that value of k will give you the order of time complexity. So that is how you should approach every time complexity problem where you are not sure. Otherwise, where you are sure, it will either be an n square or n cube. Next, and this is the last one I think, is on I star I, and I star I less than equal to n would actually mean that yeah, I think we can do it directly here. There is no point of lingering around here, and we can actually say that I star I is nothing but this will be I square is greater than n is when it will stop, right? So if we can just remove the inequality and say that we will do an equality, then of course we will get to something as this, and therefore I, when it will stop, will be equal to root over of n. So directly we can say that this will execute for root over of n number of times, right? And if you go around the bush and try to figure out the exact time complexity for this, you will see that we established that this will execute itself for root over of n number of times. Everything within it will execute for root over of n number of times, right? Now, this particular for loop, the second for loop, if you see the second for loop is going to execute itself how many number of times? It's j less than I, right? J less than I and j plus plus, right? So j less than I will execute itself for how many number of times? J less than I will execute itself. I is going to go on till root n number of times. So j less than I will go on for root n number of times. So I will have this as root n number of times, right? So that is what it will happen. So we will have a root n into root n, which is a root n square, and we will come up with an n for this particular problem. So in case this particular line item was not there, this particular loop was not there, then we would have established ourselves with a time complexity of root over of n, right? In the current state of the problem, we are actually hitting at a time complexity of n. So that is how anything can happen in terms of time complexity, in terms of the combination of statements, of programs, of algorithms, which can help you to go to a complexity class, which we have already discussed. And what we have discussed is these complexity classes. So if you see on the screen, we have discussed these complexity classes. We have discussed about our constant complexity class. We have discussed about logarithmic complexity class. Square root we discussed. We discussed linear arithmetic, which was n log n. We discussed quadratic, we discussed cubic. Exponential we have not discussed. We will discuss it subsequently when we talk about the different kinds of sorting problems. Now, you can understand that every problem can fit into this particular time complexity. And then the time complexities that we are actually looking at actually goes on like this. It increases. The time taken increases as we go down this table. Now, if you see that the values of n here define the amount of time complexity that you are going to get, right? So from a formula standpoint, if you put these values here, right, you will get these values. Now, if you see that for a constant time, it remains constant, right? In a constant time, it remains constant for every kind of time complexity problem. Now, if you see this particular area, pay your attention here. 64 becomes 256 in a quadratic equation when it goes from 8 to 6 in terms of units of time. When you go to cubic, it becomes 512 and 4096, right? And when you go to 2 to the power n, it goes the exponential root. It goes from 256 to 55,536. Do you notice here that your 2 to the power n is less than n cube when you are at 8? 2 to the power n is less than n cube when you are at 4. 2 to the power n is less than n cube when you are at 2, right? But 2 to the power n crosses n cube when you are at 16. So there will always, 2 to the power n will always be a higher number of time complexity, provided the value of n is on the larger side. When the value of n is on the smaller side, 2 to the power n will not be able to beat 2 to the power n square, or for that matter n cube. But when n is on the higher side, a stage will come when it will flip the story, and 2 to the power n will cross everybody and it will go on forever, right? And that's what we wanted to highlight from this particular complexity graph, that this entire exercise increases with the increase in the number of n, our time taken increases. And the time taken by n's cube is typically going to be highest as compared to all the rest of the population. However, when there comes a time when n becomes sufficiently large, 2 to the power n, or the exponential portion, will beat everybody. And that's what this particular graph also signifies. If you see, our 2 to the power n is here. At some point of n, input size of n, it will cross everybody. We have not been able to show that in this particular graph, and it has crossed everybody. And this graph, if it goes like this, then the time taken by them will be much higher. So if you see, if I could have drawn the upper portion of the graph, then my time complexity here, along with your n, for a 2 to the power n curve would have been looking like this. It would have been gone like this and then like this. But for our n cube kind of a graph, it would have actually gone like this, right? So it might have, in fact, this might not be correct. Let me draw it one more time. So this is your 2 to the power n. It is stable at when n is small, and suddenly spikes when n crosses a particular amount. However, when you talk about this n cube is going to go like this, right? So that's how it will go. So at some point here, we have the value of n where 2 to the power n cube, or rather n cube, is going to be beaten by 2 to the power of n, right? So that is what I tried to establish here by putting the context that yes, while we can appreciate that all these are in their orders of time complexity that we have discussed, however, 2 to the power n is going to be, the exponential complexity is going to be very large when the amount of n is very large. Till that time it happens, n cube will be the largest. And that's what this graph actually tries to bring in. That's pretty much what I wanted to cover for this session, and it has been, I've tried to create examples so that it touches upon most of the things that you will be doing in the DSA series, most of the things that you'll be asked to do, like from a stack recursive algorithm standpoint, from a sorting recursive algorithm standpoint, from a searching recursive algorithm standpoint. So I've tried to put all those loops that you will use in this time complexity lecture, so that when it comes to calculating time complexities from those programs, you will not have trouble. You can resonate to the time complexities that I have created here, and I have explained here from the context that if there is a loop which is growing linearly or decreasing linearly, it should be an order of n, and you can actually make it order of n square n cube depending on the nesting of the loops, right? And then if you see it's not growing linearly, if you see it is increasing by 2 or decreasing by 2, then of course you are hitting at a logarithmic time complexities, right? And then we have also seen that a dependent variable inside the loop can influence a root over of n, right? All of that we have seen, and all of this will at some point in time be useful when you are actually doing your time complexity exercises for the actual problems that you will solve. So these are just snippets. The actual problems will come as and when you go down the route, and there will be questions that will be asked that, okay, do a merge sort, calculate the time complexity. At that time, you will see that the loop of time complexity will match with any one of the examples that I have given. And at that time, you will see and appreciate how easy it has become to calculate time complexity. Now, I have not finished this particular module because we still have asymptotic notations and we still have linear search and binary search to do. That is why I have not done the most probable questions that can be asked. So I'll do it in one shot in the next lecture, which will cover the time complexity that we discussed here, as well as the asymptotic notations. The time we meet at the next lecture. Keep learning and happy evening. Thank you.